Well, hello friends. Welcome back to the program. Today we are going to talk about kernel stuff, and I've been thinking about something with regards to SMAP, or Supervisor Mode Access Prevention. So this is a protection mechanism in the x86 CPU that we rely heavily on to protect the kernel from being tricked into doing stuff with user space memory. So basically, it's a mode where once we turn it on, it becomes a fatal error for the kernel to try and access user space memory. And it actually has a complementary mode called Supervisor Mode Execution Prevention, or SMEP, which is controlled by a separate flag, and that one prevents the kernel from executing code that's in user space memory. So together they're quite a nice protection against many types of attack. And once we turn this on, we really don't want this to be turned off. Unfortunately, the x86 CPU allows you to turn it off again after you have turned it on, because these modes are just controlled by the CR4 control register in the kernel. So there's the SMEP bit and the SMAP bit. And we flip both these bits on if the feature is available during startup, and we never turn them off again. But if somebody were to maliciously take control of the kernel, they might be able to fashion a way to trick it into clearing those bits, and then it would be possible to get the kernel to jump into user space shellcode, for example, which we really don't want. So I was thinking about ways to prevent this, and what I came up with was, what if the code that actually writes to this register, CR4, what if we just take that code, and once we're done with initialization, we just unmap it? So kind of very similar to what we did recently with read-only memory after init. So a couple of videos ago I did this thing where we can now mark variables that will never be written to after initialization if the kernel is complete. What if we had a way to mark code this way? So once initialization is complete, nobody will ever call this function. So let's just remove it from memory and clear that out. That would allow us to get rid of gadgets basically in the running kernel that would allow somebody using return-oriented programming to update CR4. And I don't know if this is watertight, because I suppose somebody like in the compiler or linker chain might still generate like a mov something into CR4 instruction, but we can certainly get rid of these very obvious gadgets where like you have some piece of code that just writes to CR4 and then returns. So that's kind of what we're going to do today, but also I think that this makes for a generally useful thing, right? Because a lot of code will only be needed during initialization, like all of the like memory setup code, setting up the kernel page tables and stuff like that. There's a lot of stuff that we will never need to do again, and if we could just segregate all that code into a separate section and make sure that it's aligned on page boundaries, then we could totally unmap that memory. And in fact, we could even reuse that physical memory and just put it into our allocator and like use it for data at runtime. So I think I feel like this is kind of a reasonable thing, so this is what we're going to do today. And I guess we'll be starting with adding something similar to read-only after init. So this was a macro we added that you can put on variables. So if you didn't see that, let me show you what it looks like. So when you declare a variable, you can just say read-only after init, and then it gets put into a special section that we call RO after init, and then we have this code in Memory Manager that gets called at the end of initialization. Before we transfer control to system server in user space, we do this one last thing where we protect read-only after init memory. So we walk the page tables and set all of the pages in that section to non-writable. So plan here is to do a similar thing, except we will invent a new section we'll call unmap after init. But the same basic idea, unmap after init, and then we will take the write CR4. So currently we have these helpers for writing to CR0 and CR4, and actually we want to unmap both of these after, because CR0 also contains the write protect bit, which determines whether or not kernel overstepping its access boundaries is a violation or not. So we want to protect both of these. And the good thing is that we have no legitimate need to write to these registers after initialization anyway. So we'll just do this: unmap after init, unmap after init, and let's see what we can do with that. And then of course we have to teach the linker about this. So this is technically text segment stuff. So I think it needs to go within the start of kernel text, end of kernel text boundaries. Otherwise it will not be executable during boot. But we can still put it here. So start of unmap after init is here. And then the section, and then end of unmap after init is here. So I think that's going to be okay. Yeah. And then let's see if that actually comes out the way I imagine it. If we look at the sections of the kernel. Oh, right, it doesn't become its own section if we do it that way. Yeah. So let's bring it out of the text section and just put it into its own thing here. So unmap after init, align 4K at address, just our virtual address offset, and then we don't need to align it. Yeah, so I think that will be better, and then we get a dedicated section for it just for visibility. Wait, what did I do wrong here? Oh, address. Linker script, that's one of those languages that you don't get to use very often. I certainly never ever used it before working on Serenity, so I still have extremely limited understanding of it, but I know what to move and poke around to sort of get it to do what I want, but I couldn't explain it to you exactly how it works. So here we go. Now we have our unmap after init section, and it is 16 bytes, which is totally fine, given that we don't have much code in it at all, just those two write CR0 and write CR4 helpers. CR3 we don't want to unmap after init because that is the page directory register, so it tells the CPU which page directory to be using, and that's something that we change all the time, so we don't want to get rid of that one. Also, reading from these registers seems that's kind of harmless compared to writing to them, so let's not worry too much about reading. Okay, so now that we have segregated this into its own section, let's go into the code where here's where we call protect read-only after init memory. So we'll do a new one here, everything marked unmap after init becomes inaccessible after this point. And then unmap memory after init, let's say. And then I think we will copy this loop here. So unmap memory after init. Oopsie doopsie. Can I get to there? Okay. And then what do we want to do in this loop? So essentially we want to loop over all of the pages. Let's see, auto start of unmap after init. Okay. And we need to extern those so we can see them. This, by the way, is a really nifty trick. Speaking of linker script, so you can put these little markers here in your linker script where you're arranging how the linked executable should look layout-wise. And what this means here is essentially like the address that we're currently at, because this is sort of linear from top to bottom, and the address that we're currently at this point in the script, just export that address as this name. And then in your C or C++ code, for example, you can go and make an extern declaration for that name. So that's what we're doing here. So we're just saying extern flat putter start of unmap after init. It's that linker script symbol. And then we can actually use that, and we take the address of that, and then we can use that for our own computation. So it's kind of a way to communicate information about the executable layout to the program itself and encode it in the program. Very, very neat. This is the sort of thing that you very rarely need unless you're building a kernel or something extremely low level like that. Still, I find it kind of interesting. So let's rewrite this loop here a little bit, just to make it look a little nicer. And I think let's round these down to page boundaries. Page round up. Okay. And what we want to do is essentially just nuke the page table entries, just clear them out completely. So we have this helper in page table entry. So what we can do when we're iterating the page table is we can do all kinds of little things, like we can say, oh, this page is not present, or this is not user allowed, which means that it's still kernel allowed. Or you can make it non-writable, you can make it non-cacheable, non-executable. I wish there would be a way to make memory executable but not readable on x86, but I can't do that yet. But that would be really cool. Anyway, what we're doing now is we're just nuking the entire page table entry, so this this memory will no longer be there, no longer be mapped to any physical address anymore. It's gone. So unmap, disable, or unmap the, let's say unmap the entire. Boom. And then why don't we print out a cool message like unmapped kilobytes, bytes of unmap or of kernel code after init, kernel text after init, let's say. That's pretty cool. So, I guess it's like end minus start divided by a kilobyte, like that. Do we have that? We do. Cool. Yes. Okay, let's see if this boots. So, given that it was what, like 16 bytes in that section, we should be unmapping 4 kilobytes because that's the smallest unit we could unmap. But did I even call it? Here it is. Unmapped 4 kilobytes of kernel text after init. Very cool. But does it work? Let's find out. So let's take some, this is called like set groups. I like set groups. I often put random crap in there because the ID program, if you run ID, then it will call set groups to check for all of the supplemental groups currently on the account or currently in the process. But nothing else uses set groups. Or am I thinking of get groups maybe? Get groups. No, wait. How does that work? I think it is set groups. Set groups will give you the groups, right? Yeah. I think. Wait, now I'm confused. Set groups. Wait, why am I so confused by this? It's get groups that I'm thinking of. But get groups. Where is get groups? Here. Okay. Well, that almost got confusing. Anyway, get groups is really nice because only ID uses it. I don't know why I mixed it up with set groups. So here we can try to do something like we can write to CR4. And we'll just write whatever was already in there. And this should totally crash if we now try to run ID. And boom, kernel panic. That's pretty cool. So what have we done here? We have basically, we took this piece of code, write CR4, which is the only legit way in the kernel to write to the CR4 register, which controls SMAP, SMEP, and all kinds of other stuff as well. And once we got out of the initialization code, we went and removed it from the page tables. So you can no longer call it. That's pretty cool. So I think we added a nice message last time for the RO after init stuff. So let's do the same thing for unmap after init. So that when we panic because of this, we can print a cool message. So here, attempt to access unmap after init section. Yeah. So that will be our panic message. Let's see if that works. ID. Ooh, that's really neat. Okay, so let's actually take a look at the, I guess the kernel. Okay, we disassemble the kernel and then we can search for CR4 and, oh wait, start. Oh right, boot.s. So this is the very first boot code that runs. before we enter into C++ code, we run this little piece of boot code here to set up the very initial page tables and stuff, and it also accesses CR4 to enable PAE, PSE, what's that? Page address extension, page size extension. So CR4 is accessed here, and also PG, it's in CR0. Okay, so we actually do have a gadget here that moves stuff into CR4, although it's a very obnoxious gadget because there's no ret anywhere soon. And you have an LGDT and then like an L jump. So this would be it seems unlikely to me that you would get this gadget to do what you want without completely crashing the system, but even so, I guess what we could do is we don't need to return to this code, this boot code, the start code, after we have done init either. So we could also unmap this code, I think. Should be fine. But I think I'm gonna ignore that piece of code right now, and we'll just look at other CR4 accesses. So we have one here as well in APIC AP start 32, which is, oh, it's also here in boot.s. Right. Okay, so this is stuff that runs when we boot up the application processors for symmetric multiprocessing. So more stuff in this boot.s that we could also just unmap, I think. And this is also like a lot of stuff happening after here, but maybe a little more gadget friendly. I don't know. This does not look very fun either. And then you have a jump to init AP. I don't know, but even if it's not a friendly gadget, it would still be good to unmap it. Okay, so where else do we access CR4? So we have read CR4, which reads from it. Extremely gadget looking. And here is, what is this? EAX CR4. This is a reading from CR4. Oh, right, so this is when we hit some unimplemented exception trap. Sure, but that's just reading from it to dump on the debug log before we hang the system. What's going on here, though? Mob CR4 EAX. Okay, so I think what we're looking at here is that it has been inlined. And we definitely don't want that, because that means that we are leaving these types of instructions on the table. So let's make sure that write CR4 is never inline. Is that what we call it? Or maybe that goes first? Yeah. Okay. So we make those never in line, and then let's look again. So is that CPU setup? So now we can see here in CPU setup that instead of writing to CR4 with an instruction, it actually has to call the function write CR4. So that makes sure that we don't actually have a mov CR4 something instruction here. Very, very good. Okay. So let's see, mov CR4 comma. So this is in start. So there's write CR4, and then there was something here. Is this data? This is probably data. Okay, so we do have a I guess it's OF22 is MOV04, possibly one of the bits here also. So we do have at least one occurrence of that in data, but data will not be executable though. So that's fine. Let's look for OF22. Okay, so it does occur, but not many times. Yeah. Okay, so let's say it's inconclusive, but I do think that getting rid of these like super obvious gadgets here is useful, because what they look like is this, right? So we definitely want to unmap these. Okay, yeah, I think this will be good. And then of course, this, I would say this is useful as a general optimization, just to free memory that we don't need anymore after we've initialized the kernel. And also as a hardening measure, just to reduce the amount of kernel code that you can ROP into, since we don't need it for anything legit. Okay, so what do we do first? I guess let's just add these sections, and then we will do the CR004 things separately. Okay. Kernel. Add unmap after init. Mechanism for code to unmap after init. Code we don't need after init. Section, let's say. You can now declare functions with unmap after init, and they'll get segregated into a separate code segment, or separate kernel section. Gets completely unmapped at the end of initialization. This is ideal for anything. This is ideal for anything. This can be used for anything. We don't need to call once we booted and transferred. Once we booted and once we booted into user space. There are two benefits, two nice things about this mechanism. It allows us to free up memory. Entire pages of memory for other use. Note that this patch does not actually make use of the freed pages yet, but in the future we totally could. It allows us to get rid of dangerous gadgets, obviously. Gadgets like write to CR0 and write to CR4, which are very attractive, very useful for an attacker trying to disable SMAP, SMAP, etc. Get rid of, let's say, yeah, I mean, we do get rid of them. Yes. I've also made sure to print a friendly to include a helpful panic message in case you hit a kernel crash because of this protection. Cool. That's cool. Okay. And then let's mark them. Here for as unmap after init. This prevents them from this removes a very useful tool for attackers trying to disable SMAP, etc. Yes, that is cool. I like that a lot. And then let's see. So, what could we do? Like we could put this on a lot of stuff, because even stuff like the init function, we could just be like unmap after init, right? Or I guess that goes here, because that should just work. Yeah. Here's maybe it would be nicer if we could let's just like hang here so that we can see the text message of how much we freed up, and then see what else we can unmap. So really, like most stuff in this file, init finished, and it's this one is tricky, right? The second stage of init, because he's the one who calls, who ends up calling unmap memory after init. So we can't quite do that here, but maybe we could figure out a way to do that. But let's just do some other ones first. So we got those, and we can also do stuff like the setup code for kmalloc. Where are you? Like kmalloc init. There's no need for that to be callable after we have actually booted. And slab allocator init function. No need for that either. I'm just testing with random things here. Still only 4 kilobytes. I would expect it to be a bit more at some point, but let's try some other things. Scheduler initialize maybe. Let's do memory manager. Init. Oh, we can do a lot of these, like the memory manager constructor. Destructor never even gets called. This protect kernel image thing. Read-only after init. Unmap memory after init. We can't do this, right? Because we're in it while we're unmapping it. But everything else, register reserved ranges. Parse the memory map that we get from the bootloader. This is like a nice quick tour through what kind of stuff we're doing in here. And then these are all allocation helpers and stuff. There's a lot of code in here. I bet some of this could be consolidated. Okay, I feel like that was maybe everything in here. Let's look at maybe page directory. Create kernel page directory. So there's only ever one of those, and that's this constructor here. So we could mark that one, and actually let's see if it still runs. Okay, so now we're doing 12 kilobytes of kernel text. But would it still boot though? Ah, it still does. That's really cool. So we're now removing 12 kilobytes of the kernel from the address space. I really like this. This is this is really exciting for me. I don't know why. I just really love the idea of like, oh, we've run this piece of code now. We're never going to need it again. So let's just get rid of it. It really makes me wonder, like, would this somehow be transferable to user space programs? I mean, this technique. Like, is there such a thing as, like, initialization code in a user space program that you could segregate and then get rid of? Like, I feel like there's rarely enough of it, but maybe I'm like not thinking about it right. I don't know. I would have to dig deeper on that, because like your average user space program, even if you take a complex one like the browser, take our browser, right? Like we have a main function here, and if you wanted to, you could take like everything in main all the way up to when you invoke the main event loop down here. None of this code here will ever run again, right? So you could unmap it, but I feel like maybe that's not super useful. But I don't know. Maybe I'm not thinking about this right. Maybe there's something more here. So I'm gonna let that one stew in the brain for a while, and maybe hunt for a few more things we could mark here. So let's look in scheduler. I bet scheduler has a bunch of stuff we don't need. Like these are all used. Scheduler start. Ooh. We definitely don't need to start more schedulers because we can't add CPUs at runtime. So once we have initted, we should be good. And what else do we have? Initialize. Sure. Maybe I should just look at what we're calling from the init code. Epic initialize, yeah. Why not? Interrupt management initialize. Boom. And I bet you that these things that it calls out to, they can also not be called again, so that's fine. Mark. Search for M80T. Do we use that? I think we don't. Yeah, so let's just mark it. I'm probably gonna get overly enthusiastic here and like mark something that is actually used, but it's not the end of the world. We can always fix that now that we have that helpful message. Locateepic data. Who calls that? Oh, look, it's initialization. Well, wouldn't you know it? So let's mark it too. It would be cool if we could get to 50 kilobytes, let's say. It's 20 kilobytes. Okay, so what else do we have? We did epic. So once we've done all of these boot up of processors and stuff. Oh yeah, so much juicy code here just to get rid of. That is great. Init finished. Yep. Initialize timers. Sure, who needs it? Set up local timer. Calibrate, wait. Yeah, this is all initialization code. Okay. 24 kilobytes. I mean, this is like, now I'm just like slapping this thing on random things. A little bit just for fun, but Also to see what we can do with it. So I'm going to put it on a few more things, and then I guess we can... Oh, these are nice. Like the keyboard controllers and stuff like that. The virtual file system. Definitely never gonna need to destroy that, and we don't need to create more than one virtual file system. And then we have stuff like dev random, which, you know, we only ever make one dev random, or dev zero, or dev null. Oh man, there are so many things we can do this with. Dev full, the rarely used dev full. Why not the PTY multiplexer? Dev PTMX. That one is also rarely talked about. Okay, how much do we have here? Oh, I don't know why, I just want to get to 50 kilobytes. 28 kilobytes. Time management. Ooh, let's unmap that. Blah, 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 blah. So constructors are very, very juicy. Like these constructors of things that that we never destroy, never need to deallocate, those are perfect. Probing the hardware timers, excellent. Don't need those. Cool. The virtual console. Oh, totally forgot that existed. There's so many parts of the kernel that I haven't looked at in months, some of them even years, which is really crazy to say. But this project has been going on for quite a while now. And it's still just as fun, just to be clear. It's even more fun now, actually, because now there's so much stuff. So much cool stuff to work on everywhere. So process initialize, we can definitely get rid of. Very juicy. This one we already did, sure. Oh, processor class. I bet there's stuff in there we could do. Like processor initialize. Yup. Early initialize. That's even more unmappable. CPU setup. Who needs it? After init, of course, to be clear. CPU detection. Oh yeah, this is the good stuff. GDT initialization, we definitely never need to do that again. Okay. SMP communication between CPUs, I think we still need that though. I can't just get rid of those. SMP enable, like we don't support disabling it once we boot it, so we can unmap that. Okay, so that's fine. I guess we do have IDT in it somewhere. Yeah, so we can get rid of this one, which is for the interrupt descriptor table. We can definitely lose those. We also don't need to register interrupt handlers after we have booted. So I think we're good. Flush IDT, who calls that? It's during setup and initialization, sure, okay. That was a lot of stuff. 60K, ooh. But does it still boot? Let's find out. Oh, it does. That is so cool. Okay, so we have successfully unmapped 60 kilobytes of kernel code after booting up, which may not sound like that much, I guess, but and it may not be that much. Let's see how much we actually have. How big is the kernel if we strip it? 1.9 megs? Ooh. How much code is that? It's this much, so Python 1.45 megs of code. Yeah, okay, so 60K is not not the biggest chunk, but it's something. It's 4%, and we can do more. I'm sure we can do more, but as you can see here, I was really just running around slapping this keyboard on random things, and I'm pretty confident we can get that over 100K if we keep going, but I think I'm gonna knock it off here, and let's make sure that we actually get rid of that thing there that I did in get groups. Oh, I already did, I guess. So yeah, just slapping it on many things. Let's also, you know what, I'm gonna verify that I didn't actually break the SMP boot. So let's test that. SMP has booted. And we have 2 CPUs, very cool. Okay, so I didn't break that. That's cool. Great. Okay, I think we'll just commit these. So kernel slap unmap after init on a whole bunch of functions. There's no real system here. I just added it to various functions that I don't believe we ever want to call after initialization has finished. This patch frees up with these changes. We now were able to free up 60 kib or unmap. Yeah. So that's really rad. That's super cool. Yeah. Oh, I wonder. Maybe we don't need these. Prepare for idle loop. Wait, who calls that? Post init finished. No, okay, I'm not gonna mess with this anymore. We did enough for one day, but I'm very happy with this because I think we have come up with a nice new thing for the kernel to be able to free up memory and to protect ourselves against SMAP and SMEP bypass or protect against somebody disabling those by wrapping into our control register write gadgets. So nice progress, I would say. Yet another mitigation in the bank. So I think we'll end the video here. If you made it this far, then I thank you for watching and for hanging out. And I hope that you saw something interesting here. I definitely enjoy doing this kind of thing. I've just been stacking so many mitigations lately, but I think when I hear from people who are trying to write exploits for Serenity that these mitigations are actually getting in their way and that it's frustrating them and their attempts, that is really fun, and it really motivates me to add more of these things. So that's cool. Anyways, I still very much encourage people to try to break the system's security. I really, really love hearing from people working on exploits for Serenity, or just trying to hack it in whatever way. It is super interesting, and if you're doing something like that, I would love to hear from you. And if you're interested in working on mitigations, I would love to hear from you as well, what your thoughts are, because I'm just learning this as I go, and I'm no expert, although I would love to become one, and I think by doing these things we can all learn and become experts. Anyway, that's enough of me talking. Thank you very much for hanging out, and I will see you next time. Bye.